Welcome everybody. My name is Dr. Gaston Baudat, owner and president of Innovations Foresight. Our company is active in the field of astronomy and optics. This video is a presentation of our latest patent-pending technology for doing wavefront sensing using AI or artificial intelligence. The idea is to access a wavefront without a wavefront sensor, such as a Shackhartman or a pyramidal sensor. Instead, we use a camera. Although this presentation revolves around astronomy and telescope, the technology itself is not limited to this field. It has a broad application in optics. So how can we retrieve the phase from an image? How does it work? Well, let's have a look with a star. In this case, it's a star with no turbulence, no atmospheric turbulence, no seeing for now. We'll come back to the seeing aspect later. And if I take an image in focus of a star, I get this typical diffraction limited pattern. You see a peak, and you don't see very well here because it's so dimmed and it's difficult to spot. There are rings around it, diffraction rings. This is the airy disk, the classic airy disk for a circular aperture. When you look at a point source far, far away like a star, the incoming wave is a plane wave and give you this diffraction pattern if everything is perfect in the telescope and there is no seeing. Now let's add some aberration in a system. Let's say I'm going to add +3 waves of spherical third order. Well, in that case, I get this kind of shape where I have some of the diffraction ring now much brighter and everything is spread. And that's the result of the spherical aberration. Quite a lot here. Now, if I add -3 waves of the same kind of aberration, I get exactly the same pattern. Meaning I cannot say from the image if it's +3 wave or -3 waves. I lost the sign information. I lost part of the phase information because the PSF here, at best focus or defocus, is the amplitude, the modulus of the Fourier transform of the phase. And in the process, you lose the phase, unless you do something about it. What can you do? Well, you can add a bias. That's known as phase diversity. In this example, we're going to add 10 waves of bias in terms of defocus. A defocus is an easy one to add because you don't need any optical part. You just have to move the sensor plane away from the focal plane by some distance. And this way, you can create some level of defocus. When you add defocus in a perfectly diffraction limited image, you get this kind of example where here we have 10 rings because we have 10 waves of defocus bias or phase diversity. So let's see what's happened if I add now +3 waves of spherical like I did before. Well, you can see now I have a blur version of this one, a little bit bigger, with some gradient of intensity. It's a bit brighter in the center than in the edge. And if I add -3 waves, well, I get a totally different picture with a pretty bright ring here, and everything is tighter. So obviously there's a big difference now between -3 wave and +3 wave when I use my phase diversity trick. And that's the way the system works. By using the right amount of defocus, we can spot many different aberrations and we can retrieve the wavefront from them because we can solve the ambiguity problem we had without any bias. Okay, now let's see how we can leverage this phase diversity trick to actually retrieve the wavefront from a practical standpoint. So here we use AI to do that. Well, first I should say that our goal was to have a very quick, accurate, efficient way to get access to the wavefront every time we get an image. We don't want to run any optimization algorithm at runtime. We want to do the hard work beforehand, once for all. It may take days or weeks to solve the problem and train the neural net, but when it's done, we have a feed-forward neural network, and the calculation is done in a millisecond, which is very useful if you want to do very fast kind adaptive optic, for instance. To solve the problem using AI, what we do, we express the wavefront with some kind of tool. And so in this case, we use Zernike polynomials. That's not a limitation. We can use different ways to express the phase. We need to express aberrations and then translate them in PSF, defocus PSF, to feed the neural network during the training phase, provide us at the output the value of the Zernike coefficient used for each of the polynomials. That's the idea. So you can see here in this block diagram, how does it work? So we pick a range of Zernike polynomials to fit our problem. So we have more or less, depending of how many level of aberration we are looking for. And for each polynomial, we have a coefficient which is taken in a range at random, a range also defined by the application. In general, we use annular Zernike polynomials to take care of the case where you have a central obstruction. So from those random numbers, let's say 10, 15, depending on how many of the Zernike polynomials we use, we build a wavefront with some level of aberration. To that, we add the aperture function, which is typically a circular pupil in our example, with some level of central obstruction, if any. And of course, we add the phase diversity, the bias, the power, to create the defocus. Using scalar diffraction theory, we can now compute the PSF, the one you saw before. In this one, you can see it's high resolution PSF. You can see we have some level of astigmatism here and probably some level of coma. Those PSF, we make 100,000 millions of them. They are after that scaled to the level expected for the neural network, and we feed that to the neural net. And we tell the neural net during the training process, output the Zernike coefficient used to create this image. After removing the power, we have the actual wavefront and therefore the aberration related to the PSF at the input of the neural network. That's the process. We can add more on the process. We can add seeing effect or other kind of noise, and we can even output the seeing level here to get a seeing estimation from the image itself. And that's what we do when we do the training for some level of seeing. We build a bench to test the concept. It's a small bench I can carry easy with me for demonstration. And I'll do a demonstration at the end here on the bench. So let's talk about the bench. The bench is made of a cemented achromat, is roughly an inch in diameter, 300 millimeter focal length, which gives you a f12.5 system. The source is made of 7 pinholes of 10 microns. They are basically artificial stars. The pitch between pinholes in the focal plane is 1.5 millimeter. The goal is to be able to analyze the wavefront at once from the signal frame on axis and off axis across the field. We use a white LED to do the illumination of the pinholes. And we have a beam splitter, a 50-50 beam splitter. And of course, there is a camera on the back. So here, you see the block diagram of the optical system. There is the achromat. Basically, this is like a telescope. On front of the achromat, there is a very nice flat mirror, very flat, such it doesn't create any aberration, at least if I don't do anything about it. On the back of it, you have the source here with the diffuser and the pinholes, the 7 pinholes, and a beam splitter. The light is reflected by the beam splitter and goes straight to the achromat, and then is reflected by the mirror and comes through the achromat again. So we have a double pass test, and the light goes this time through the beam splitter. We have a color filter, usually a red, because in most applications for actual star, we want to minimize the seeing, and red, longer wavelengths, feature less seeing. And then we have the camera. Here the camera is at focal plane, but in reality we're going to move the camera a little bit behind the focal planes for the phase diversity. And this is the bench with the flat mirror, the achromat, this is basically a telescope, the beam splitter, XY stage to adjust the position of the source, the filter box, and the camera. I can give you some idea about how good the technology is, and that's something we have done almost a year ago with my friend John Hayes. He went in 4D, his former company, to do some tests with a twin-man green interferometer, which is a digital interferometer with very high resolution. It's a bit a golden standard here. To compare on the same bench, the one you saw, the performance, using this kind of tool, who cost 100K, and using our phase diversity technique. The phase cam uses a red laser at 633 nanometer. And in our example with a bench, we use a red filter at 656 nanometer H alpha, 6 nanometer bandwidth. It's not exactly the same wavelengths, so we may have some variation because that is close enough, and also the bandwidth is tight, so we should have close to monochromatic situation. And be aware, the technology doesn't need monochromatic, but here we want to compare with a phase cam, which is monochromatic. So we build all the model monochromatic for that matter, and we can compare. So on the left, you see the phase cam with its divergent lens. Let's have a look to some of the results we got with this experiment. In this example, we use a single 10-micron pinholes with the red filter I was talking about. The neural net was trained for a 10-micron pinhole in a monochromatic condition to match the situation with a phase cam. All the results are in milliwaves. Here you can see the wavefront as a color heat plot. And red are peaks and blue are trough of the wavefront. This is the AI solution, and this is the phase cam solution. Both use Zernike polynomials to rebuild the wavefront. Here, the phase cam use the interferometric data, the fringes, to do the work. And here we use the defocus image of the pinhole. It looks pretty same. Remember, we may have some difference between both of them because it's very hard to align everything exactly the same, and there is a small difference in wavelengths. On the right, you have a table with the level of milliwave error found by the AI solution for this bench and from the phase cam. In that case, we have a flat mirror with no aberration. We have just the achromat, which is supposed to be close to perfect. We are in very good agreement. The maximum difference is 25 milliwave for the third order astigmatism. Considering we have slight difference of wavelengths and we are not perfectly aligned, I've done some tests lately on a Shack-Hartmann instead of a phase cam. Use a Shack-Hartmann wavefront sensor. And I found with the latest model, and being very careful to align everything the same, that we are roughly at 5 milliwave of maximum error. So this tells you how good the technique can be. That's an interesting experiment done by John Hayes on his telescope. He has a 20-inch telescope, which is now in Chile. And it turns out he measured his telescope with a phase cam in the lab in double pass. So he has some data about the quality of the scope. The goal here was to compare those results with an actual star in the sky. Now we know stuff may have changed between the lab and the sky, but this gives you an idea about how sensitive and accurate the technique is anyway, even under seeing limited conditions. So what you can see here is the results from the phase cam in double pass of the wavefront. You see the central obstruction. And this is the result from a defocus star in the sky with the seeing. It's not the same color plot, but we look at the same kind of structure. We have those three kind of red peaks, which are a sign of trefoil. And trefoil is a sign of slight pitching of the optic, probably the way the first mirror is attached to the telescope. Is not much. So the telescope is still a diffraction limited, but we can spot that much error. And this error is already seen over here by the phase cam. So if you look at the overall result, the AI show about 7 milliwave of RMS error overall across the wavefront for a Strel ratio of, let's say, 80%. But the phase cam in the lab gave us 65 milliwave, so very close, RMS, for a Strel of 85. So they are in good agreement in terms of quality. And this is coming in the lab from averaging 512 frames with the laser to minimize noise artifact in a lab condition. This is a single frame taken in the sky. This is a very interesting example, I think. What you see here is raw image at intra and extrafocal, before and after the best focus. And we defocus by the phase diversity in both cases, 4.4 millimeter roughly. And you see here intrafocal -4 and extrafocal +4. We are on axis with the star for the analysis. Those are the two images, and you can see some level of spherical because they don't look the same, and they should look the same. It's not much spherical though. Again, this telescope is obviously diffraction limited. And those two images are simulations coming from the AI solution. How did we get them? Well, what we did was we took the Zernike coefficient, built the wavefront error from the Zernike coefficient from the neural net using those image, or one of them. So the neural net saw only this one. That one was taken for the sake of comparison. So using this information, we rebuild the wavefront using the Zernike coefficient from the output of the neural net. And from there, we defocus by the known amount and rebuild the PSF, adding the estimation of the seeing value, because the neural net can output that. We create the seeing level to blur the image by the same level of seeing, including scintillation, and we have even simulated the diffraction spikes of the spider. And here you can see those are very close to the actual one. It's a little bit sharper, more contrast, because this is a monochromatic solution, and this is a polychromatic one. Another interesting thing before I jump to the live demonstration is this aspect of the capability of the technology to do field-dependent analysis at once. You see, what you're going to look at on the raw image coming from the bench are those 7 pinholes, defocus, and I have 7 along a line. We can measure the wavefront at once for all of them, because we have all of them at the same time in the frame. And you could do that on the sky if you take an image of a star field. You get all the aberration in the field at once. This is an example of field curvature, which is a kind of aberration, and that's the level of defocus in microns of the, basically the focal plane is not a plane, it's a curve, which is common. But the red one is the actual expected field curvature for this achromat using the Zmax model we have for the achromat in a monochromatic situation. And over here, you see the value coming from the 7 pinholes using the phase diversity AI technique. We retrieved the defocus. And so we are looking at the same shape. Not exactly the same value for a couple of reasons. First, this is monochromatic, this is not. We use a red filter, yet it's not totally monochromatic. So you have probably some kind of chromatic aberration. The other one, the achromat, has probably some tolerance in manufacturing. So we don't know exactly, because we haven't done the measurement. But you see, we get something very close, and we get all of that at once, without any part in motion, moving any sensor and doing anything, take only in a single frame. My last slide before the live demonstration with the bench is to talk about Skywave. Skywave is a software specifically designed for telescope alignment or collimation, and also analysis of the overall performance of the optical system. Skywave comes in different flavors, but in its basic form, it will provide user information about the quality of the optic in a quantitative way. You take a defocus image of a star, and the system will tell you how much aberration of any kind you may have, coma, astigmatic, and so on and so forth. And you can use that to turn the knobs to adjust the alignment of the mirror until you get the right level of performance, like the good Strel ratio. This is the optical bench we're going to use in the coming demonstration. So this part here is basically a telescope. In front of it, you have the achromat I was talking about before in the presentation. And in front of the achromat, there is a flat mirror. This is a very good flat mirror. This is a thumb screw at 45 degrees who can be used to create some level of stress to the mirror. And that stress will create some level of aberration, as you will see on the coming demonstration. So far, the screw is not pushing against the mirror, so there is no stress. Over there, you have an XY table with the source made of 7 pinholes and a white LED. This is the beam splitter, and on the back of it, you have a filter here inside this box. It's a red filter, and then the camera. The camera is set such we have some level of defocus to match the need for the model which was used to train the neural network. Here we see the raw image coming from the camera from the bench every few seconds. You have the frame counter on the bottom here. Those images are sent to the neural network for processing, and we get the Zernike coefficient from the output. It takes few seconds not to do the calculation from the neural net, but to get the frame and process it. This is a Python code which is not compiled, so it's slow a bit for that matter. It's just a demonstration software. But if you compile everything, you can go at video rate kind of things. So yeah, you can see the 1, 2, 3, 4, 5, 6, and 7 pinholes, artificial stars, defocus the right way for the neural network used in this application. The yellow cross is the optical center of the optical bench. And the on-axis pinhole here is known as pinhole 0. And you have pinhole 1 here, 2 and 3, and -1, -2, and -3. All those pinholes are aligned along a line, and they have a pitch of roughly 1.5 millimeter between each pinhole on the focal plane. So this is the wavefront of pinhole 0. You can see over here 0. You get the wavefront in red peaks, in blue trough. If you look here at the scale ratio, is 98.4, almost 99%. So we are, we are way diffraction limited. I mean, it's a pretty good optic. So on top of here, you have the defocus value in microns from the focal plane at the circle of least confusion. We are only 40, 50 microns to the actual target for the neural network. But the neural network was trained with tolerance on this, so it doesn't need to be super accurate anyway. You see the RMS total wavefront error is roughly 20,000 of a wave, and the peak valley, the PV value, is around 90,000 of a wave. You can see here the summary of the basic aberration. You have astigmatism, 15 milliwaves RMS, 3 milliwave RMS, threefold very little, 1 milliwave RMS, and you see the 7 milliwave RMS for the spherical, which is close to the actual Zmax model for this achromat. So we have a little bit some astigmatism, maybe coming from alignment or maybe a little bit from the mirror. I just don't know, but it's so little, then it doesn't matter much. We are almost perfectly diffraction limited. So now let's move to pinhole 1 and then 2 and 3 up, because moving away from the optical center of axis means we'll see more aberrations. The spherical aberration is not field dependent, at least if everything is well aligned. But you should spot more astigmatism here when I go to the next pinhole up. See, if I go to pinhole 1, you start to see some increase on astigmatism. Spherical remains the same, everything else is small. We are now almost at 20 milliwaves. Go to pinhole number 2. Now we are 3 millimeters away from the optical axis, and we get even more off-axis astigmatic aberration, which makes totally sense. We are at 30 milliwaves now of astigmatism. Everything else is still low, as it should be. Pinhole 3, we are now at 4.5 millimeters away from the optical center, pretty off axis, and we get almost 40 milliwave of astigmatism. You can see the strail drop to 94. It's not that bad, but it tells us we have scale astigmatism because I'm moving along the vertical line. So if I go down and do the same thing with the pinholes below the optical center, below the pinhole 0 on axis, and I go to, let's say, -3, you see I have pretty much the same level of astigmatism at -3, which is expected since it's a symmetrical system with this achromat. Okay, let's go back to pinhole 0. We can see from pinhole 0, the PSF, which is pretty good. Take the square root of it, you get better idea of the diffraction rings. And you see it's perfect. Of course, the strail ratio is almost 99. So now my next step is going to warp the mirror by turning the thumb screw I was talking about before. That's a screw at 45 degrees on the side of the mirror. So if I turn it, you will see live what's going on. Now we see a pretty large amount of astigmatism. Look at how elongated the PSF has become. We have even some level of coma coming from the stress on the mirror by the thumb screw. Pinhole 0, wavefront, strong astigmatism at 45 degrees. You see now this astigmatism is very large. It's 10 times more than he was at the situation of the flat mirror almost. Now we are at more than 0.1 wave, 140 milliwaves, a huge amount. And we see some coma and some trefoil, which is typical of a pinch optic. The spherical is still in a few thousand of a wave because it's not coming from the mirror, it's coming from the achromat itself, so it doesn't matter if I warp the mirror for that matter. The system can separate all of that. It's a wavefront sensor, it can retrieve all the aberrations for themselves. The strail is not very good, it's 48, you see? And the next interesting things to see would be the PSF. So the PSF looks pretty bad. The strail is below 50%, and I have this typical sign of astigmatism balanced by defocus. I'm at the best possible focus position, minimizing the circle, the circle of least confusion here. I guess the square root gives you a better idea, and you see astigmatism with some level of comma. Let me show you what the neural networks actually sees. That's what it sees in real time, is the pinhole 0. It's cropped around pinhole 0 for the calculation of the wavefront of pinhole 0. And this is what is reconstructed from the output of the neural network using the Zernike polynomial. That's a monochromatic reconstruction, so it's a bit sharper, but it has the same shape as you would expect because we capture the wavefront error, the aberrations. Thank you very much for watching this video. I hope you enjoy it. If you have any questions, feel free to contact me anytime. Here is my email, gaston@innovationsforesight.com. I will be happy to read your email and answer your questions. Thanks again.